The time to review our semester-long data project for Data Science 620 under the instruction of Dr. Mahanama. Our team members, Nish Patel, Shashank Patani, Townsend Hurst. So picture yourself here, you're trying to figure out the best way to avoid this, some form of an arrival delay, and you want to figure out the best airline to fly into. So that's kind of the goal of our project. I'll get into that more here in a second. Project layout, we have our table of contents, which matches everything off to the left here side. So you can click on any of these to get to any of these sections as necessary. So like I said, our goal, predict historic arrival delay. Basically, how can we predict a arrival delay? So we initially set out to build a tool that could predict whether a departing flight would be delayed, but the available data from the Bureau of Transportation Statistics linked here only reports arrival delays only at an aggregated level, not by individual flight. So because of that limitation, we shifted our scope to specifically arrival delays for Reagan, Dulles, Richmond, Norfolk, all in the state of Virginia with the air carriers American, Delta, Southwest, United. Used 10 years of data spanning from June 2015 through June 2025. And our raw data set included 21 columns listed here. Primary interest was in the Bureau's definition of delay, arrivals of 15 minutes or more behind schedule. So during our exploratory data analysis, we created box plots, line graphs, heat maps, trying to understand trends. And throughout the course of the project, we used multiple packages, libraries. All of those imports are all listed here. So as we created those different graphs, we found ultimately that for the most part, it seemed that we really need to create a new metric from the data that was given. And so we created the arrival delay per flight metric listed right here, which essentially normalized the data and allowed us to see much more clearer patterns and trends because it allowed us to compare direct relationships between the different airports. Because some of the other airports like DCA, Reagan, or Dulles had more flights, therefore more delays. So we wanted to compare them fairly. But with that, we started creating heat maps, and those seemed to show us the best trends. So we compared each individual airline and airport. I won't talk through all these for the sake of time, but you can see what we started to notice with a lot of them is post-2020 over here, and really in the summer months here between May and September, it seemed like delays really started to increase. And I'll just scroll through a couple of these just so you can kind of see. And, in some cases before 2020, it was the same. But yeah, you can see that. And obviously there are some outliers there as well, like listed here. But that was kind of our idea of some of the trends that we notice. So with that, I'll kind of skip ahead here to our analysis. So we, before moving into time series type approaches, we approached two traditional machine learning models, both the random forest and the XGBoost. Our workflow during this phase, we combined all the CSV files listed up here. We cleaned missing values, one-hot encoded the categorical variables, generated aggregated delay metrics, and then we ultimately split the data set into what we discussed throughout the course here of a 70% train, 20% validation, 10% test subset. So that's how we split up the data. And then we trained separate random forest XGBoost regressors to predict the total arrival delay here. When we actually ran to evaluate this model, though, we found something a little bit unexpected and unrealistic. Ultimately, was an R-squared value of 1.0. So that was not exactly what we were hoping for. We thought initially that was great, but realized that's just not a realistic expectation. So we reviewed it and realized the models were basically memorizing the nature of the data and weren't really discovering meaningful aviation behavior. So because of this, we had to kind of rethink our plan, revisit, refine our feature engineering. And so coming down here, we went with this updated Ceramex model, which I'll talk through in a second. But coming down here, one thing we noticed So we thought through feature engineering. Their original data set stored year and month separately, and the year sometimes appeared as a float. Values like 2025.0, which caused parsing issues in downstream models, especially when we were working with a formal time index. So because of this, we explicitly converted year and month to integers and built a proper timestamp column. This ensured that we basically had a continuous, reliable timeline. So once we did that, we also added these new seasonality features, and that was in conjunction with those heat maps, see if maybe what we kind of notice as trends could actually be modeled and maybe get us a little bit more of a realistic R-squared value. And then we created the two targets for classification and regression, which are listed here. So we restricted our models to features that would be known prior to the flight's arrival, so that we would ultimately ensure no data leakage. And as we ran through this with now adding the seasonality features, we found, I'll skip through kind of our prediction summary here and just go straight to the charts because I think that gives the best picture. But we ultimately found just significantly more realistic R-squared values. You can see here for Dulles, Reagan, Richmond, and Norfolk. You can see these two obviously a little bit lower than the two busier airports, potentially just with more flights here, a little bit more data to work with, and fewer flights here, less data to work with. But like I said, the R-squared value much more realistic. And then we can see here in our regression accuracy, looking at that random forest model now with some seasonality features that, the parsing fixed as well. You can see, obviously not perfect, but we can see a much more realistic picture. And then using the Ceramax model, we can see actually a pretty decent forecast that is created that for the most part, in all cases, follows the trends. Now you can see, obviously it's not going to increase to the extent of the delay for most of them, really not going to hit the full peak. And main thing we're thinking is that with the nature of aviation, some delays, some of those peaks could be something maintenance driven, could be just something unforecasted that we may not be able to fully predict. So the model is going to be a little bit smoother than some of the extremes that you may see in the nature of aviation. But all that being said, we felt a lot better after running this model. And kind of our last effort with this project was to create just a small, basically two tools to use. And we'll kind of cover in the conclusions in future work, but that would be something we'd like to expand on, just something to really help the user figure out the best airport to use, best airline to use. And here, this one, we're just predicting arrival delay. So you can select the airport, the airline here between Delta, United, Southwest, American, predict the month and the year, and just hit predict delay. And here you go. You would just get a picture here. Normal operations are expected. And we also use just a historic flight recommendation tool. Now, granted, this is just using historic data, but you can select the month, hit the find best flights, and then get your best option here in the state of Virginia, just looking at 4 different airports and the particular airlines that we analyzed. And that would tell you, the best airline to potentially minimize arrival delay. So ultimately, future work's conclusions, we felt like as a whole that we really learned a lot through this project, really pushed us to grow in our understanding of exploratory data analysis, data wrangling, model evaluation, classification, regression analysis, and helped to learn a lot about the different nature of the aviation domain. Here are some of our references just to develop some of that domain knowledge, as well as the data set that we used. And then unused exploratory analysis, like I mentioned before, is all listed at the bottom. We thank you for your time.